Good morning, everyone. My name is Kuba Yezmanovsky. I'm a graduate student here at the University of South Carolina, and today is an extra lecture on top of our last 3 weeks of the workshop. This is part of the 2025 Bioinformatics and Data Science Workshop sponsored by the SCINBRE and AI Institute of South Carolina. The goal here is to bring together the last 3 weeks of information into these digestible steps that you can then take and use with your own data. So we distributed to everyone this augmented version of the Wisconsin breast cancer data set, and we'll be using that today from step one of cleaning it up, formatting it properly, and then all the way to creating our own models in PyTorch. So really the big goal here is to lay out the steps and the framework for doing this yourself. Now, in real life, this might take anywhere from weeks to months and be a bit more meticulous, but we'll try and obviously do it in a bit of a faster fashion, but while also noting all the important details, and then you'll be able to build off of that yourself. We have this structured in about 3 segments, and each of those kind of correspond to what each of the 3 weeks covered loosely. In the first segment, we'll talk about cleaning up our data, importing it using pandas and NumPy, and then saving our data. In the second part, we'll look into building some scikit-learn models. And then in the third part, we'll try and build our own neural networks using PyTorch. So, with our goal being to understand how to apply everything we've learned over the last few weeks, there will be some reoccurring themes throughout this and really important topics that hopefully you guys take away from this. So, one of them is this idea, and it's, emphasized, people say it differently, but a great practitioner and neural network researcher, Andrew Karpathy, likes to say, become one with the data. And what we mean here is you really want to understand your data, what the features represent, and know why you're using it, why you're using certain features, why you don't use other features, the distributions of your features, to understand all of this before you start moving into building your models, because then when you run into issues, you will be properly informed to resolve those issues. And then another big important theme that we hope you guys take away from today is this idea of failing silently or being really questioning of all your results. So you'll find that often in data science and machine learning, you can write code that will run. It will not crash. You won't have a syntax error, but logically, it is not doing what you think it will do. And that will lead to a lot of issues, right? So maybe your model's underperforming significantly. Then you should question why. Did you structure your data properly? Maybe you shuffled it wrong. Did you normalize it? Maybe you didn't save the normalized version. Maybe it's, doing 100% on the test set. Then something also, you should have alarm bells going off. And then frankly, even if it's performing as expected, you should still be questioning your results and going back and making sure you did everything correctly. So there's these two reoccurring themes that we'll talk about throughout today's lecture, and hopefully you guys leave understanding that those are very important as you move forward with your own data. So without further ado, let's jump right in. So you can see here I have my own VS Code folder opened up that I'll be working in today. Now, throughout the workshop, we've worked in Google Colab and locally on our own machines, so everything I do today will be able to be executed and run in Google Colab. So as of right now in my folder, I've just got this README TXT file and also the CSV file that we have sent out to everyone and will be using. So first, as part of becoming one with your data, let's make sure we truly understand what we're doing here. So we have a classification data set, and there's two classes. It's binary classification. Each sample is either malignant or benign. And then we have these features, these attributes that we'll be using to help us classify each of the samples. So let's create a new file here called clean data. So first thing we want to do is import pandas, and then we'll create a data frame from our CSV file. So first thing we do, we've imported our data. Now let's take a look at the first 5 rows via df.head, make sure that it makes sense. Because looks good to me, but sometimes you might have a CSV file that has the first few rows containing some metadata that you don't want to include in your data frame. So we could do that via the skip rows. So if we did skip rows, it would skip some of those rows before reading into our data frame. We don't want to do that in this case, but just something you want to check after importing your data. So we've got the head. Now let's take a look at the tail of this data, the last 5 rows. So it looks good. We've got the diagnosis column at the end as we're expecting, which is what we'll be classifying, the two classes we'll be classifying into. We've got all these features. Now, notably, we're not displaying all the columns because there seem to be more than than the notebook wants to display. Now, some interesting things. This unnamed column, or named unnamed, seems to be just a replica of the index. So we'll note that and likely drop that column later on. But let's go on. Let's use df.describe to describe all of our columns. Interesting. Now, again, note, we're not showing all the columns because there's more of them. There's 33 of them, and we're only displaying a certain subset of them. Now, to properly look over your data, you should check every column. Now you can do that by going, now I want, to look at column mean area. Now, notably, we don't know what some of the names of those additional columns are, so we can check that via df.columns. And here we go. Looks good. We can see that it stops displaying after this column, so the next column to follow would be mean symmetry. Well, let's just look at the describe of mean symmetry. And you can do this for all the columns, and when analyzing your data and looking over it the first time, you definitely should do that. Make sure that everything makes sense. Now, this is when it becomes a data set specific problem. So you would work with the individual that you collected the data with. That might be you, maybe a collaborator. And understanding your data means going through these columns and making sure that the values, the percentiles, the means make sense or what you expect. Because if not, then maybe there's some conversion that needs to be done, or maybe you collected your data wrong. So being aware of all of this at every step and double checking, having these sanity checks is really important. So we know our data is properly structured, so we'll move on to the next step. So since this is a classification data set, we know that each of our samples has to be either benign or malignant. If it's not, then we cannot use it in training. So let's see all the unique values that are present in the diagnosis column. So interesting. So we've got benign and malignant as expected, but we also have this NaN type, which seems to represent missing values. Now, that's a bit problematic because we likely won't be able to use these rows, but let's investigate a bit further, see how many of these missing values there are. So there's a few different ways we can do this. let's do it this way. So we've got this we've got this array of the unique values in the diagnosis column, and then we'll use some list comprehension to iterate over all of the possible rows. So we'll go for every possible diagnosis in this row of unique diagnoses. So it would be benign, malignant, and NAN. We'll do this. We'll go check the data frame at diagnoses and check if it's equal to diagnosis. And if it is, this will return a Boolean mask of true and false values over that data frame column, and we'll sum the values. So the true values will equal to 1 and the false values will equal to 0. So this way we get the sum for every single one of these unique diagnoses. Now you can see we've got 239 benigns, 399 malignants, and 0 NANs, which seems interesting, right? Because how is that a unique value if it's never present there? So this is where you step back and you start to ask some questions. And you'll run into many of these situations as you work with pandas and cleaning up your data, or even sklearn and Torch. Now, this is a great time where you could go to one of the chat models and explain to them what's going on and your confusion, and they might be able to help. But we'll look at it a bit differently here. We'll start from the ground up and go, well, this NAN type, and I know from prior experience, so this is where some prior experience is helpful, but we give you the guardrails today, and you'll be able to build off of that. So we'll import NumPy as NP, and NumPy is this NAN type. So np.nan is that NAN type we're finding in our column. Now, what's interesting is we're saying for each of these unique values, we check which diagnoses are equal to it, have a Boolean mask, and we sum that Boolean mask. Now, if a diagnosis is NAN, it should return true here, right? NAN should be equal to the NAN type. Let's double check that, because if that's true, then we're making a mistake somewhere else. If it's not, then it's an issue in this. And interestingly enough, np.nan is not equal to np.nan. And this is because the NAN type is defined to be unequal to everything, including itself. So that's something, we as practitioners might know because we've done this over and over, but you pick these little tidbits of knowledge up the more you do it, but there's plenty of resources out there to help you as you stumble into these issues and get confused. But luckily, the pandas data frame has a method called isNan. So we'll call that, and that is a true or false mask across all the values where it's NAN. So we want to remove all the diagnoses that are NAN. So when the diagnosis is missing, it's NAN. So this would return true in that spot. We want to drop those because we won't be able to use them for classification. So let's do is NAN, but we want to do that across the column diagnosis. And now we have a Boolean mask for the diagnosis column. And now we can sum this, and we get that we have 3 NAN values, right? Now, it's interesting to note, and this is one of those moments where you can make a mistake, but it will run, but not as intended. So sum is adding all the values, and truths are ones, falses are zero. But what if we did count? Because count seems like a reasonable thing to do. But you see, count returns 641 because that's how many rows are present in our data frame. It does not do summing, it counts how many rows are present. Now, while these seem somewhat similar and might be easily confused, they do different things, but both will run. So again, you want to always have these sanity checks. You want to always be making sure that your code is doing what you expect it to. So our code is telling us that we have three NaN values in the diagnosis column. Now we know that the length of our data frame, we have 641 values. So if we subtract, and we can set this array equal to counts, the value at counts at 0 is equal to 239. Counts at 1 is equal to 399. So if we subtract those two values from our length, we should expect the three missing rows that are NaN, and sure enough, that adds up. So again, we did a sanity check, just making sure that everything that we're doing adds up, so we don't inadvertently do something that we didn't expect. So now that we know this, let's drop all the rows that have a NaN in the diagnosis column. So this gives us true where it is NaN and false where it is not NaN. But we want the opposite because we'll use this to mask into the indices. So if we go as such, now it's true everywhere where there is a value and false where there is no value. So we'll use this to index into the data frame. And again, we're not assigning it to the data frame to save these changes yet. We're doing a sanity check. So we'll check the length of this, and this should be 638 as expected, because now this is the data frame minus those three rows. So we've double checked everything. Now let's assign our data frame equal to the new data frame. So data frame length of our data frame is now 638. All right. So now let's move on to the next step. So as we were looking into our data when we first imported it, we saw that it had this column called unnamed :0. And that column was just a replica of the index. And we don't want that at all, right? Because we already have an index for each of the rows. We don't want to duplicate this. And then when later on we look for duplicate values, this will screw things up for us, because if there's a row that has every column value the same except for this index value, it will return as false because it won't be identical, except in reality it is, because this unnamed column is a duplicate value of the index. So let's drop this column. We can do this by using the df drop, and then we specify which column, and we want to make sure it is correct. So we'll just copy it straight from there. And sure enough, now the data frame is properly structured without the unnamed column. Now, note again, we have to reassign this to the data frame. We didn't do this at first because we want to make sure it executes properly as expected and then assign it. So we'll go back here and assign it. And then, yep, looks good. All right. So now that we've dropped that column, let's check for any duplicate values. We can do that using the duplicated method, and it arrives. So this is the row is the row already present in the data frame true or false? And you can see we've got some trues. Now we want to know how many rows have duplicates in the entire data set. So let's just sum, and we get 15 rows that are duplicates of at least another row. Now, this is where you can ask yourself a context-specific question, and it has to do with the data set and the domain you're in. One, what does it mean to be a duplicate, and are duplicates acceptable? They might be in your case, they might not be. Maybe the way your data is structured, you're expecting to have duplicates. But this is where we can go back to our README and also think back to what we know about our data set. And we know that in our data set, duplicate rows are not acceptable, right? Because each row has a patient identification number and then these features associated with that reading. So we should not have duplicate readings from the same patient. So we want to make sure to drop all of these. We're going to do df.drop duplicates, and you want to do that. And then let's, again, sanity check before we reassign it. Length of this plus 15, because we're expecting it, and that's 638, as we had in our data frame up here after we dropped the NAN diagnoses. Our data frame was of size 638. Now, after we drop duplicates, it should be 638 minus 15, which it is, right? Because 638 minus 15 is 623, as is our data frame right now. Sweet. So again, sanity check worked. We know we're doing the right thing, so we'll assign it back to our data frame. And then let's just print out this for ourselves. So now we've, done some good cleaning up. We've removed the rows that didn't have a class. We've removed the unnecessary unnamed column, and we've dropped rows that are duplicates of themselves. Now, there might be some columns and/or rows that have missing values. So let's check for those, and then we'll think about how we can deal with those. So for column in df.column, right? So if we just print the call, this will print out the name, the name of each of these columns. But we want to check, is there any NaN values? And if so, how many? So we can do that a few different ways, but let's go out of our for loop and just take a look here. So df, and we'll look at the mean symmetry column. So for the mean symmetry column, dot is NaN, we'll return a Boolean mask, and now we want to sum this to get the count of missing values. So we'll take this code, but use it here. So we'll do df at the column, and then isNaN.sum. And that returns the sum of missing values for each of the columns. Now, it'd be a bit more informative if we had the column name along with it, so we can get a little fancy here, do some F strings, and then we'll do print out the column name, space, colon, space, and then print out the number of missing values. And sure enough. All right, so now we know for each of the columns how many rows have missing values for that column. Now let's look how many rows have any missing values, right? So we looked down the columns. Now let's look across the rows, or down the rows across the columns. So to do this, we will go and look at, so df dot is NaN, as we've seen, is a Boolean mask over all the values. Now, we want to say for each row, how many missing values are there? Now, that is equivalent to walking across the columns, and the columns are represented by axis 1. So we'll do sum across axis is equal to 1. And now we get for each row how many missing values it has. But as we stated, we want to know, we care about how many rows are missing more than one value. So there's the rows that are missing 0 values and those that are missing at least one or more. So we'll do greater than 1. So now this returns a Boolean mask on top of that, where true is if it's missing more than one, and false is if it's missing less than one. Now, let's change this to 0 because now it'll be a Boolean mask where it is true for any row that's missing at least one value. So we'll sum this, and that means we have 54 rows that are missing at least one value. And now comes the question, what do we do about this? And this is a problem-specific question, a data set-specific question, because there's a bunch of different ways we can deal with missing values. So we can try and fill them in some ways, and there's built-in methods and pandas for this. You can fill it in with the value from the row above or the row below. Now that doesn't particularly make sense for us in this context. You could fill it in with the mean value from that column, or if it's a categorical variable, you could fill it in with the mode, right? But in our case, for this problem, we'll just drop these rows. We just don't want to deal with a row that has at least one missing value. If it has a missing value, we're going to drop that row. So we can do that by going and saying df.drop NA, but now we need to specify, is it the columns that we want to drop? So if a column has a missing value, we drop it, or a row. And we want to do rows. So we'll look here at the parameters, and it says you specify the axis as 0 if you want to drop rows which contain missing values. So we do axis is equal to 0, and we have now dropped the rows, and we see we have gone from 623 to 569. So 623 minus the 54 rows that we found to be missing values is 569. Good, that passed that sanity check. Now let's just double check that we're not missing any values here. So we'll do is nan, and then we'll take a look at that. Now we do sum across axis is equal to 1. And then do greater than or equal to 0. And we'll sum this. And it's 0 as expected. Great. So we've passed our sanity check. So let's go back here and assign the data frame equal to our data frame after we've dropped all of the nan rows. Sweet. So we've pretty much cleaned up our data set. Now, if you were working with your own data set, you'd probably want to spend some more time with it. Now, this is the data set that we know the changes we've made to it, so we've undone those. But if this is a truly raw data set you're working with, you want to spend significantly more time making sure that everything makes sense before you start doing ML or any models. So we've pretty much cleaned up our data set. There's only a few things left to do. One of those is we want to standardize or normalize our data, right? There's a few different ways you can do that. We will do min-max scaling in this case. Then we also want to shuffle up our data set because when they were creating the CSV, who knows, did they add all the benign patients and then the malignant patients? Or, there's many questions there. So we want to shuffle it up randomly one time and then save it that way so that we have reproducibility every time we start to train a model. And then obviously we'll want to train test split our data. And as we've mentioned over the last 3 weeks, particularly in week 2 and 3, how you split this data is really important to your problem, right? If you split your data to where both your train and test set contain information about some participant, and then you get good results and you go around claiming that your model can now perform well on unseen participants, that is, it's just false, right? Because your test set contained information that your training set had because it trained on one individual and it also got tested on that same individual, even though those might have been different samples, but they both came from the same individual. Not saying that you can't do that, right? You can, but you must acknowledge that that is what is happening. So we'll talk a little bit about that later, and we've talked about it in the past, so that's really important. So we'll split our data according to the way we want to for our training purposes here, and then we'll save that data. So we've got our data set. Now let's let's turn it into the X and Y matrices. So, right, so we know that for models, for ML models, and for our neural networks, the data we structured, at least for classification, in this way, where we have an X matrix, where each row represents a sample, and each column is the value at a different feature for a different feature. And then we'll have our Y vector, which contains our classes. So in this case, it'll be malignant or benign. Now, we also know that we want the Y vector not to be the strings malignant or benign, but rather 0 or 1 representing the two classes. And then we also know that in the X matrix containing our features, we don't want to have this ID column. Now, how do we know this? Well, if we read our TXT file, it tells us that this is an identification number, and we know we don't want to use that to help us classify. We want to use the features describing the tumor to help us classify this cancer rather than some patient ID. So let's create our X. X is equal to the data frame, but we'll drop the columns corresponding with diagnosis and also the ID column. And now let's print this out here so that we get our sanity check. All right, that looks good. Now, this X is still a data frame and we'll want it as a NumPy matrix. So let's use the .to NumPy method. And now our X is a NumPy matrix, a NumPy array. Let's use .shape to, again, have a sanity check and make sure that it's in the proper shape. As expected, we have 569 rows, but only 30 columns because we're not using the ID column and we're not using the diagnosis column. So we've created our X. Now let's make our Y. Y is equal to DF, and we want just diagnosis. So we've got this data frame. Now we know we want it as a NumPy array, so we'll go to NumPy. But as we noted earlier, we want this to be a vector of values 0 or 1 corresponding to the two classes, not a vector of the words benign and malignant. So we got to convert this into 0 and 1 somehow. Now there's a few different ways you can do this. You could do the apply method for data frames, and we'll create a function. So you pass in a function, and we'll create a lambda function here. And this function will be applied to each of the rows individually. So we'll do 0 if benign, and then else 1. And now that works. If you don't like it doing it that way, you can do it a different way. So you can go y is equal to np dot where. And so now we're using a function that comes from the NumPy library. And here we'll specify df dot diagnosis. So we pass this in and we say where it's equal to benign, then set that value 0, else go 1. And then that will work as well. And we don't have to do the toNumPy method here because why? Because we're already using the NumPy library, so it auto turns this data frame series, it automatically turns it into a NumPy array. So now we've got our X and Y. Let's do a sanity check here. So we'll go X dot shape and Y dot shape. All right, looks good. The rows are matching, the 30 columns of features, and this is just one column of 0, 1. Sweet, sweet. We're looking good. So we've got it in the format we want it, but we want to make sure we do the normalization of our data next. So to do so, we'll go X is equal to X minus X dot min, and axis is equal to 0. Now, why do we do axis is equal to 0? Because the 0 axis is all of the rows, and we want to go across the rows. So we want to normalize for each column, right? If you wanted to normalize within each row, then you'd do axis is equal to 1, meaning you'd go across the columns. But we want to go across the rows and normalize for each column. So we'll do that. And we'll divide by x dot max, axis again equal to 0, minus x dot min, axis is equal to 0. Looks good. Now let's double check the shape. Looks good. So our sanity checks are passing, so we'll assign x to this. So now we go down here and we have our normalized x, we have our y, we've scaled them. Now let's shuffle them up. A few different ways to do this. So one way is we can permute the indices and then reshuffle them using these permuted indices. So numpy dot permute, you have to use a numpy random. So numpy rand dot permutation, and then we'll go 32. So you see, so what this returns is from 0 to 31, it shuffles that and returns a permuted array of these values. Now we want it to shuffle the length of x. So now we have our permutations, but as you can see, every time we run it, it uses a different random seed, and we want this to be reproducible. So we'll do numpy dot random dot seed 42, so that now every time we run it, it uses the same seed and it's reproducible. So it isn't that we run this notebook again sometime and we get different values in our train and test split, different values at different places in our matrix. So it's important that we use a random seed for reproducibility. So we'll do indexes underscore perm array. So now we want x is equal to underscore perm index. So we've now take our x value and we reassign it each row according to these permuted indices. Now it's important that we rename it because if not, we would end up every time we run this, we'd reshuffle it. And maybe one time you go through this notebook, you note run the cell twice by accident, save these, and then a different time you run it once, and your saved data will be shuffled differently. So this is one of those small mistakes where, right, see how the values change, but if we do x underscore perm and rename that, then you'll see the values don't change. Now, in both cases, the code ran, but in the first case where we didn't rename it, it was one of those silent failures where you might down the road, a month from now, rerun something and then everything falls apart and you sit there scratching your head. Well, I have no errors. I think I did everything right. What's wrong here? And this is what you did wrong. So you've got to really be careful about these small details so that you don't make mistakes like this. So we've permuted and shuffled up our x. We need to make sure we do the same for the y. So y underscore perm is equal to y, and then we'll do index perm. Sounds good, looking good. So we've now shuffled it up, and the last thing to do is split up our data. So to split up our data, we want, let's say, about 80% of our data for training, and then 20% for test. So we have 569 samples times 0.8 is equal to this. Now, that's not a full sample. That's 0.2 of a sample there at the end. So let's convert this into an int. And then, so we'll use the first 455 samples for training. So train underscore len is equal to this, right? So train length. So x underscore train is equal to x underscore perm. We'll take the first 455 values and we'll do x underscore train dot shape as a sanity check again. Now, we need to do the same for our y. So y underscore train is equal to y underscore perm, and we'll take the first 455 values, and then we'll go y underscore train dot shape to make sure, again, we have a sanity check. We're looking good. Now, so we have the first 455 samples for training, and we want the rest to be for testing. So we'll copy this here, and then we'll go train test. Now, this is one of those moments where, again, you can make a silent failure, because if I do this, it runs just fine, and then we go x underscore test dot shape and y test shape. Sure enough, everything's running just fine. But this is maybe where the more you work with this, you'll have some flags and some alarm bells go off. It's unusual that if we split our data set 80-20, how is our train and test set the same size? And you'd be asking the right question. And that is the issue here. So we took the same samples for both train and test. What we need to do is start at index 455 where we left off for the train and use the rest for testing. And now this looks better. Now, as I noted, you saw in that case, the code ran just fine and it didn't give us an issue. Now, hopefully you've been sitting here and realized maybe been starting to question, why is our code here with running except the variable is undefined, and that has to do with how notebooks work. This value must have been defined earlier in a cell we ran, then we might have deleted that cell, but it's still saved in memory. So never ignore these yellow squiggles, and it has to do with the fact that we misspelled perm up here and then spelled it correctly down there. So we want to make sure that it's um, always spelled correctly so we don't get these issues down here. So let's restart our notebook just to be clear. We cleared out and run all the way from top to bottom. And now we're getting an error here because this prem variable we defined earlier and then we fixed it, but it was still saved in memory, is causing an error. So we'll make sure that we name it correctly. And sure enough, we're getting good results. So now all that's left is to save our data. NumPy has this nice save function that we can use where the first argument is the name of the file. So we'll name it x_train dot, and you have to end it with the NumPy extension. So it'll be npy. And the second argument is the name of the object in your code. Now we want to save the x and then also the y, and then we'll copy this and then save our test split 2. So we've saved them nicely. Now I'll comment this out so we don't run it again. And you can see that here in the file explorer in my folder, I have these nicely saved. And we can now move on to the second part, which will be building out some basic ML models in sklearn. But before we do that, I just kind of wanted to note, I hope, you get this general framework of what it looks like to look over our data, clean it up, and a real big emphasis on being meticulous about it, right? So you saw how misspelling something or using the same variable name over and over can lead to unintended consequences where the code will run, but down the road, you'll get results that you are questioning, unsure of. And we'll see that theme reoccur here, and we'll continue to, try and be meticulous about it, and also we'll show what can happen if we are not careful about the way we go about things throughout this whole process. So we've just finished preparing our data. And now that we've saved it in a format we want it to be in, we can use it for machine learning. So we'll create a new notebook here to keep everything separate. And in this notebook, we will build off of the things we learned in week 2. That being using the built-in modules and models from sklearn. So we know that we need NumPy because because we saved our data as NumPys. And then we will also go from sklearn.tree, import decision tree classifier, and then plot tree function so that we can visualize our tree. These are both things we used in week 2. So first thing we want to do is import our data that we just saved. Now I'll copy this code here because this will save us some time. Now, there we go. That looks good. That looks like the same shape we have over here. So we're almost ready to start training a model. Now, let's note that this is something that we've harped on a lot over the last 2 weeks, this idea of information leakage. And it can come in different forms. One, as we've noted before, is sharing information between the train and test data sets that could be the same type of participant is in both data sets. But another issue that is far worse is optimizing on your test set. So what we're about to do, and you'll see that there's this pattern, is we train our model on our train data, then we evaluate it, and then we might update our hyperparameters. If you remember, those are these attributes of our model that are not learned from the data, but we, as the ML researcher, will tune these parameters. So we'll train, evaluate, and then tune our hyperparameters, train again, and evaluate. Now, the question is, what are you evaluating on? So if you train on your train data set and then you evaluate on your test data set, and then you go back and tune your hyperparameters, and then you train again and to evaluate on your test data set and go back, tune your hyperparameters, train on your train data set, evaluate on test, and you go, oh, I'm done. I like these results. You wipe your hands dry and call it a day. You have, violated the first assumption that we had about our test data set. That assumption being that it would always be held out. We wouldn't use it until we finally decided on a model that we liked, and only then would we evaluate it on the test data set. Because by doing this outer loop, you're doing this outer optimization loop as the human, because the inner loop is the model and algorithm learning on the trained data. You as the human now are doing this outer loop where you are seeing how the model performs on the test data and then updating the hyperparameters according to that, thereby leaking information about your test data into your model via your updates of the hyperparameters, which now results in invalid results when you go and say, hey, this is how my model performs on unseen data, aka your test data. Well, it's not actually unseen data because you performed this outer optimization loop. Yet, we still need to update our hyperparameters somehow. So to do so, we will further split our train data into a training set and a validation set, or a dev set. It's not same thing. So to do so, let's borrow the code we just had over here and further split our train data. So we've pasted this code here. Now, for our train and dev sets, let's make the train set a bit smaller. So let's do 75% rather than the full 80. So we'll do 75-25 split, and let's run it. So that looks good, except thankfully we have this sanity check. Like we've been saying to, at every step, always make sure that everything makes sense. And something doesn't make sense here. So our dev set has 0 samples in it, and it shouldn't be that way, right? So our train length is of size 341, and that adds up with our train data. But 455 minus the train length is 114 and not 0. And yet we're seeing 0 in our dev set. So let's take a look at our code here and see what's going on. And the issue here is we're reusing xtrain. We take a slice of it, we take 341 of it and assign it back to xtrain. So now xtrain only has 341 samples in it, not the full 455. So then when we say we want to assign everything after 341 to the dev set, there is nothing left to assign. Hence why the dev set has 0 samples. So with some proper naming, we can fix this. So we'll go up here and rename train to be train full. So all we did up here was just name it to be full, and then we'll go up here and go full, right? And now we're making sure that we have different names and we're not reassigning the same value back to itself. So we rerun our code, sure enough, it looks good. So now we're ready to create our first model. So we'll go just for, so make a decision tree, a D tree first. So let's call it decision tree classifier is equal to decision tree classifier is equal to decision tree classifier. Now you can see there's different hyperparameters we can specify, and we'll go back and specify these in a second. But first, let's make sure that the random state is equal to some number, right? So this is similar to when we were shuffling our data. We want it to have the same random state for reproducibility. So it's not that we rerun our code and we get different results. Is it due to the hyperparameters or we had a different initialization? So we'll have the same initialization here, hence why we have this random state. So we initialize our model, and now we need to fit the model to the data. So we go decision tree.fit. And for this, we need to pass in X train and Y train. So we have now fit our tree to the test data, train data. And now let's evaluate it on the dev set, see how well we're doing. So decision tree dot predict, and we'll pass in xdev, and this gives us some predictions, but let's assign them to a variable called pred. If we want to visualize it, we can call it pred over here. And now we have predictions on unseen data, right? So our model was trained on X train, Y train, and now it predicts on XDev. To evaluate how well it's doing, let's compare it to the YDev. Now we can look here. Some values look like they're properly predicted, but we can see that there are some mistakes, but we want a more robust way of comparing this. So as we learned in week 2, scikit-learn has a metrics module, so we can go from scikit-learn.metrics, import, and we'll use the confusion matrix display and the classification report. So let's see here, classification report. And it tells us that it takes in Y true and Y pred. So our Y true is Y dev, because those correspond to the true values of our prediction, and our prediction is pred. Now, this doesn't look that nice. Luckily, if we wrap this in the print statement, it'll display much nicer. So we get an F1 score of 92%. That's not too bad. Now, let's go here and look at our confusion matrix. And we want to display it from predictions. And again, it's Y true, so dev Y and Y dev and then pred. And this is our confusion matrix. Not doing too well or too bad. Now, this is where we've done one kind of step of this optimization loop. So we've passed our train data through, we've evaluated on the dev set, and now let's go back up and update our hyperparameters. Now, one cool thing about decision trees is we can visualize them. So they have this explainability aspect to them that some other machine learning models might not have. So we'll do plot tree, and we'll pass in our decision tree classifier. And we can see this is what our tree looks like. Now, looks pretty deep. And as we learned in week 2, the deeper the tree, the more prone it is to overfitting. So let's go up here and adjust some of our hyperparameters. So let's see what we can adjust. So this gives us the signature of the function of the class. And we can see these parameters and attributes we can specify. One of them is max depth, which by default is set to none. Let's see what happens if we set it to 4. We set it to 4. Now we have a new tree with a max depth of 4. We fit it to the train data, and then we predict, look at our classification report and our confusion matrix, same deal, but the tree is a little less deep, but maybe we can do a little bit better. So let's go back up here and adjust our hyperparameter. Again, let's see, what if we do max depth 3? So run through this code again, and then, well, we see we're doing a little bit better. We got 1 percentage point better on our F1 score, and our confusion matrix looks better. Now, we'll combine some of these so that we can run them on one line. And this is what our tree looks like with a max depth of 3. Now let's take a look at what max depth of 2 looks like. So it looks like this. Let's see the results. Oh, we're doing even better. So let's, keep following this trend. Let's see what the max depth of 1 looks like. So that's our max depth of 1, and we have now gotten worse results. So let's go back to max depth of 2 and stick with that. So this is going to be our decision tree. Now, these aren't bad results. One could be more robust with their hyperparameter search. You can do a grid search algorithm, a random search algorithm, and check out some of the other hyperparameters. But we'll move on to random forests next. So for a random forest, we'll go and import from scikit-learn.ensembles, because this is an ensemble method since it's a group of many trees. We'll import random forest classifier. Now, you'll see that there's this reoccurring pattern here. So we initialize our model, we train it, we evaluate it, then we update the hyperparameter train, evaluate, and update hyperparameter train, evaluate until we're satisfied. So again, random forest classifier is equal to random. This is a markdown cell, so we'll make a code cell. Random forest classifier is equal to random forest classifier, and we'll pass in some hyperparameters later, but we'll start off by making sure that the random state is equal to 42. So we have now created our random forest. Next, let's fit the random forest. So we'll go random forest classifier.fit, and this looks very similar to the code as in our when we were creating our tree. X train, Y train. Now we'll do random forest classifier dot predict on xdev, and we'll check that runs. Now we'll set it equal to pred. All right, so now we can evaluate. So we'll go up here and borrow some code. So let's see how we're doing. So right off the bat, we're doing pretty good with this random forest. 94% F1, and that confusion matrix looks pretty nice. But as we noted, we have some hyperparameters we can adjust here. So let's see how those will change our results. Now, before we change anything, there's one thing to note. So while this being an ensemble method might make it more useful in some applications where you care about overfitting, so you can see that we're doing better here right off the bat, it loses some other aspects, and there's trade-offs here. It is less explainable. So in the decision tree case, we could easily print out the decision tree. In the random forest case, it's not so simple because it's an ensemble method of 100 trees. Now, you could, in theory, print out each of these 100 trees, but it wouldn't be as simple and explainable of a method as a decision tree is. So go up here and we'll take a look at some of the things some of the hyperparameters we can tune here. Now we have max depth again. We also have this n estimators and a few other hyperparameters. So we'll start with max depth. So max depth is equal to 4. Let's go through and evaluate. Okay, results have not changed. Now let's go through and remove this to kind of streamline our code here. Max depth equal to 4. Let's check about max depth equal to 3. No results changing. Max depth equal to 2. No results really change. And let's do max depth equal to 1, and we do worse. So let's just not mess around with max depth. Looks like we're not getting much better results with that. Now let's change this n estimators. So by default, it's 100 of these trees. Let's see what happens if we set it equal to 10. So better than max depth equal to 1, but not as good as when we had all 100 trees. Change it to 50. Not bad results, somewhat similar to 100. So because 50, our model will be smaller if we have 50 trees versus 100, then we'll leave it at 50 since we get similar results to 100, and that will be our random forest classifier. So you now see how this becomes somewhat of a structured process. You initialize the model, you train it on the train set, you evaluate on the dev, you update your hyperparameters, and in all these cases, you could do a more robust search of hyperparameters than we're doing here, but you're getting kind of the gist of it. Now, let's see what it would look like if we trained an MLP. So 3 MLP. Now for an MLP, we'll have to go back up here and import it from scikit-learn. So from scikit-learn.ml.neural networks, import MLP classifier. So from their neural networks module, we'll import the MLP. Now I'll go over here and borrow some code so that we don't have to type it all out, and we'll talk through it together. So you initialize it just the same as you would with a decision tree or a random forest, but it's got some different hyperparameters. So you can see here, and this all relates to the things we talked about in week 2 and 3, particularly in week 3. So the model has an input size of 30 because that's how many features we have, and an output size of 1 because we're doing binary classification. And then we define it to have one hidden layer with 32 neurons. It'll train, so look at the train set, then update its weights for 32 for 20 iterations. And again, we're specifying this random state so that we have this reproducibility. It will not stop early, and we have an initialization for our learning rate. So let's create this. Now let's do the same thing we've been doing before. So MLP dot fit, and we'll fit it to the train data. So X train, Y train. We have successfully fit our MLP. Now let's get the pred. So pred is equal to MLP dot predict on dev X. Does this look sense? We're doing a sanity check as always. The pred looks good, so let's evaluate it. So we'll go and borrow some code from up here. And take a look at that. So not too bad. There's some things we could adjust here. So let's see, what if we add another layer to our neural network? So we right now have it 30, 32, 1. What if we add another hidden layer with 16 neurons? Fit our data again and evaluate our performance. Okay, looks like we're doing somewhat similar to the random forest and our good decision tree. Now, what if we double the amount of neurons in each hidden layer? So we'll go 64 here and 32 and evaluate our results. Well, that's pretty good. That's definitely the best we've seen so far. Now, keeping in this direction, let's see what happens if we keep increasing our neuron count in our hidden layer. So let's go 500, 500, and our results get a little worse. So let's go back to our 6432 setup, and these are the best results we've seen so far. So we've tried out 3 different models and had this loop where we train on train data, evaluate on the dev set, update hyperparameters until we get a satisfied model. Now, we've trained on this MLP and we seem to be getting pretty good results. So now let's bring in that test data set we've held out and see how well we perform on that test data set. So we'll borrow some code from here and we'll predict on X test, and let's call it test pred. So let's take a sanity check, make sure our test pred looks good. Looks good. Now let's again go here and borrow some code to evaluate how we're doing. Now we know that this is no longer the dev set, it's a Y test, and let's predict. And we sit here and we go, well, these results aren't too good. 49% macro, I mean, we might as well just be flipping a coin. And this is what we mean by code that will run, right? And we've been harping on it for since the first notebook, and now we're on the second one. We'll keep talking about it, the third one, because these little issues, if you're not careful, they'll come to bite you. Because you see here, the code just ran fine, but because we forgot to change this pred to test pred, then we're getting these nonsensical results. Now, you'll go and say, hey, this is, a contrived example. And in fact, it is in this case. But if you're not aware of these small things that can happen while training models, they will come to bite you. So, you always want to stay vigilant and, like we said, question all the results if they're doing worse, better, or even as expected. Double check your code, make sure you're doing everything correctly. So now that we have assigned the variables properly, let's look at our results. And sure enough, this looks pretty good. An F1 score of 96% is not bad at all. We know that class 0 from the previous notebook was benign, right? So we set 0 to be benign and malignant to be 1. So we're not missing very many malignant tumors, which is pretty good. So we have successfully trained 3 different models, and even more importantly, hopefully you kind of understand that there's this structure to all of this. It's a bit formulaic in some sense. So that kind of concludes this notebook. Now, all these models have different strengths and weaknesses as we've discussed over the last 2 weeks. And if you want to start using neural networks much more, then you'll see that this code right here is very unsatisfactory. It leaves a lot to be desired, and that's where Torch comes in and notebook number 3. So now for notebook number 3 with neural networks and PyTorch. This is going to be a fun one. But before we dive right into it, I wanted to note that neural networks are really good at unstructured data, and our tabular data by definition is structured. And also neural networks thrive in the domain of lots and lots of data. And our puny little data set here with only a few hundred examples is very small, and you might be better served trying to do something along the lines of a decision tree, random forest, or XGBoost. All, we looked at those in notebook number 2. But we'll move forward with this data set in this notebook, namely to just lay this foundation of what it would look like to train a network from scratch in PyTorch. And then you have these pieces that you can go on and use yourself when you have your own data that is hopefully bigger and better suited for using neural networks. Dive right in. So we'll import Torch. And we'll also import torch.nn as nn. And we'll also import numpy because we will have to use it to load our data. Now we'll go over here to the top and borrow this code right here for loading our data. And then we'll also borrow it again for splitting our data. So let's run all of this, make sure it looks good. These are the same numbers as we had before in the previous notebook, so that's looking good. Now, notably, before we move forward, PyTorch works with tensors and not NumPy arrays. To you and I, this conceptually is the same idea of matrices and vectors, but they're represented a little differently lower level in the computer. So we'll have to convert all of these NumPy arrays to tensors, and it's very simple. You would do something along the lines of, tensor is equal to torch dot tensor, and then in here you could pass in an NP array, right? But rather than writing all this out by hand, I'll just quickly borrow this code so we don't have to look at all of it. So we don't have to write it out all by hand. But this is what our code will look like. Runs just fine. And note, I'll do this, and we'll come back around to this later. But I'm removing this, which won't cause an error. Won't cause an error, but it will lead us to an issue later on down the road. But I wanted to remove this so that when we run into that, and if you ever run into that issue yourself, you'll know what's going on because it's a very common issue in the beginning of training. Well, it's a common issue all the time, but you might not fully know where it's coming from in the beginning. So hopefully we remove it here, we run into this error, and we'll know why we get it in the future. Now I'll quickly just paste this line of code again. It's really simple, right? We're just printing out the shape of our train XY, dev XY, and test XY. Again, a sanity check. We just want to make sure that everything looks right. And sure enough, it does. So let's move forward. So we have imported our data. Now we need to define the model. Now, in our previous notebook, we saw that defining a model in scikit-learn is as simple as this. Now it'll be a little bit more complicated in Torch, but that's because it allows you to have more control of what you're doing. So we ended up with this model with 62 hidden layers, 6432. But let's start off with that original model. Let's create that original model we had that had a hidden layer of size 32. So you have to create a class. And we can name it whatever we want. We'll call it simple MLP. And it needs to inherit from nn.module. And then it has to have two methods. The init method and then the forward, which will take an argument and return something. So just sanity check, right? Let's make sure that at least we've defined it correctly first. So we'll go model is equal to simple MLP, create that, looks good. All right, sweet. Now let's see what happens if we try and do a forward pass through our model. We get an error, and it's because we forgot to specify self in our forward pass of the model. So it's important. It's a small detail, easily forgettable, but you always have to specify self because it's a class in Python. Now, sure enough, we're passing 5 in, and it's returning 5 as expected, as we defined in the forward pass. So now let's go back to our model here and keep moving forward. So we know how we want our network to be structured. The input layer has 30 neurons, right? 30 features. Then the hidden layer is 32 and output layer is 1 because we're doing binary classification. So it'll look something like this. We can call our first layer L0 and we always refer it to our self because this class represents the model. So self.L0, so the first layer, we want to define this first layer and we do it as such, nn.linear And now we have a linear layer, and we have to specify, as you can see, the input and the output features. As we just talked about, our first layer will take 32 and output, or it'll take in 30 and output 32. And then we have the next layer. We could call it L1, but because in this case it will be our output layer, I'll just call it self.out is equal to NN. And now these linear layers have to match up. So it has to take in 32 and output 1, right? So again, we have our input layer, our hidden layer, and then our output layer. Now, we're missing one thing. We're missing actually a few things, but we're missing our nonlinearities. We have to have our nonlinear activations. We spent a lot of time talking about those in week 3, so we're going to have to define them here. So we'll go self.relu is equal to nn.relu, and then self.sigmoid is equal to nn.sigmoid. So now we've got the two nonlinearities we want to use. Now, granted, we could choose any of them. We could use all sigmoids if we wanted to, but I want to use ReLUs in the middle of our network. So we have defined everything we'll be using in the init. That's what we do. We define the structure, but then we use that definition to create the forward path in the forward method. So we'll do x is equal to L self dot L0 of x. So we take our input x, pass it through our defined L0 layer, first layer, and assign that value to x. And then we do that again. So we'll do x is equal to self.out, self.out. And we'll take this x that we assigned over here, pass it through self.out, and assign it back to x, and then return x. Now we're almost done defining our model, but the last thing to do is we have to then use our nonlinearity. So we'll wrap this layer with a self.relu, and we'll wrap this layer, our output layer, with a self.sigmoid. And now we have properly defined our model, and we can take model and try and pass 5 in. Now you'll see we get an error because 1, it's expecting a tensor input, and 2, it's expecting the input to be of size 30. So let's first create a tensor that'll match this size, and then we can pass it through, again, as a sanity check, make sure we're defining everything correctly. So we will create a tensor of size 30 to have this sanity check. And we can do that via torch.rand random int, and then we go low, high, and then size. These are the parameters we'll pass. So we'll go low is 1, comma, high is 10, and then size is equal to 1 by 30. And we can see the shape of this. So 1 by 30, and then again, it's a random answer with values from 1 to 10. Well, not inclusive, but nonetheless, now let's pass this value into our model. We'll go and then model, pass in the input. And now we're getting another error. Let's see what we're getting here. So we're trying to do matrix multiplication, and they must have the same data type, but got long and float. So let's go up here and see input dot d type and see what we get. And we get int 64. So, and this is where we'll pause and note, and this has to do with that piece of code we removed earlier, and we'll run into that issue and fix it the same way, is that when we define the weights, when the model is initialized, when we initialize it right here, the weights in the model are initialized as type, data type of float 32, not int or long. So we got to make sure that our inputs are the same type. So we'll go dtype when we're creating this dtype is equal to torch dot float 32. And now we'll see that our input data type, the data type of our input tensor is float 32, and it will successfully pass through this. And you see we get an arbitrary value of 0.692. Sweet. So we've created our model. We've done some sanity checks to make sure that everything adds up. Now that we've created our model, we need a few more things. So we need to define our loss function. So you can do that via, and the standard thing to name your loss function is the criterion. So we'll go is equal to, and then nn dot, and this will give you all the loss functions. Now, notably, we can also look at the Torch documentation here. So if we open up Chrome and we open up a new tab and we go Torch loss, look at some Torch loss functions. We can go to the Torch documentation that I highly recommend, going to if you ever have any questions. We can see this is the torch.nn module that we imported in the beginning of our file, and there's a bunch of stuff here, but we're interested in the loss functions. And you can see they've got many different built-in loss functions, but we'll be using binary cross-entropy loss. So it defines the loss function here and some parameters you can pass into it, and then it specifies how to be used. So you need to initialize it as such, and then you pass in first your pred and then your target value. So we'll go back to our code and implement our binary cross entropy loss function. So nn.binary cross entropy loss. There we go. So we've got our loss function. We've got our model. Now the next thing we need is something to update the weights, right? So as we talked about at the end of week 2 and into week 3, this model will take the forward pass given your examples, and then we will compute the loss, and then we want to update the weights in such a way to minimize the loss in the direction of the gradient. And we'll get the gradient from this loss function, but the optimizer in PyTorch is what will update the weights. So you can create let's create our optimizer. We'll go optimizer is equal to torch dot optim from the optim dot, and now you can see there's many different optimizers. We talked about how Atom and SGD are probably some of your best bets in week 3, so we'll just run with Atom over here. Now, unlike the loss function where you can specify some arguments and parameters, you have to for your optimizer. Specifically, you have to pass in the parameters of the model you want to optimize. Otherwise, the optimizer won't know what weights to change. So we'll pass in model dot parameters as the first argument. And the second argument is, you can see here there is a default value, but let's at least set it so that later we know we can change it, which is the initial learning rate. So we have defined our model, defined our loss function, defined our optimizer, and we're pretty much there. So let's take a look at model when we pass in xtrain. So we get an error. Now this error looks a bit familiar to some of those errors we were getting earlier, and it has to do with the different data types. We're again getting double before we were getting long, but it doesn't match up with the float. And let's check here. xtrain.dtype. And sure enough, it is of torch float 64 and not 32 like the model wants. So we got to make sure we fix that. So I will just go back to our import here, and we will quickly change this as such. Now, this will work just fine. So we can clear this output and run it again. And sure enough, let's see the shape of this. So our X-train has 341 samples in it, and our model output is 341 by 1. So that's exactly what we want. Now, let's take a look at it. As expected, our model weights were randomly initialized, and we just passed these numbers through. So we're getting values centered around 0.5, but it's a meaningless result. So let's call these our predictions. So pred is equal to this, and then we can go back here, pred. So now we want to, as we've always talked about, pass our inputs forward and compare our predictions to our true values and compute the loss. So we'll go criterion, and as you remember from the online Torch documentation, you first pass in your predictions and then your target value. So we'll pass in pred, and then the next value will be y train. And we're getting an error again, right? So as you can see, we're rolling through this. There's some errors, but we're figuring it out. And hopefully this is a useful, you know, useful video for you guys, because these are the errors you will run into when you first start importing your data. But let's take a look at this error and see what's going on. So it doesn't like that the sizes are different. It says that one is 341 by 1 and the other one is 341. Please ensure that they have the same size. So again, let's go back up here, create a new cell block and go pred.shape. All right, and then let's do ytrain.shape. All right, so we see the issue here. Now, Torch has a cool unsqueeze function. So we'll go unsqueeze. And it wants us to pass in the dim. We're going to unsqueeze. And we're going to unsqueeze the 0 dim. My apologies, the first dim. Anyways, point being now is the shapes are proper. So let's copy this right here and use it over here. Now, notably, unsqueezing the Y train over and over and over again, because you'll soon see that this block of code we repeat is inefficient, likely be best up here to unsqueeze your Y train once rather than doing it over and over. But for now, we'll leave this in this code as a, inefficient block of code. Anyways, you can now see that because this is the last line in our block it's returning, and we can see its output here, the loss of our model. So sweet, we're doing well. So we'll assign that to the value of loss. And then we want to propagate our loss backward. So we'll go loss dot backward, and this will update the graph, the tree that represents the weights of our model, and the loss will be backward propagated. Now, the last thing to do is update these weights so that each weight is associated with some loss, but the optimizer is in charge of actually updating the weight. So we have to do optimizer dot step. All right, so it steps in the direction of the negative gradient. Now we can go here and look at loss. So we'll run this block over and over and you'll see the loss will decrease, but we want to look at the loss as it's decreasing. So we'll do loss.item to print out the loss. Now, notably, what is the item part is you saw that when we printed out the loss, it was this whole object in Python and it had a gradient value and things of such sort. We don't want to deal with that. We want to just pass that loss object backward, back propagate it, but then we just want to see the loss, just the value itself. So this .item method will access the numerical value of the loss itself. Now we're almost done. And these 5 lines right here are going to be the essential lines of your training loop. Now we will go and add some bells and whistles, and you can see afterwards that there's, plenty of bells and whistles that you can add, but this is the core minus one thing. We're missing one important thing is when you pass the loss backward and you do the optimizer.step, you have to then clear it. Now, this is just a function of how the PyTorch library is set up, right? But when we pass that loss backward, if we don't clear the loss before we pass the loss again, then it will all start to double up. So we have to go up here and do optimizer.zeroGrad. So now these 6 lines right here are going to be your bread and butter. This is how, we train our models. And from this, you'll build better and more robust training loops. But let's take a look here what this does. So this is that loss value. Now let's run it again and again and again. And you can start to see our loss is decreasing. Not very fast, but it's decreasing nonetheless. So we've got from 0.6 to 0.5 to 0.4 to 0.3. Now, let's just print out our preds just to see what it looks like. So we're getting more meaningful values, or what we can only assume to be more meaningful values as the loss goes down. But that right there is everything, right? We've created a model, defined our loss, defined our optimizer, and have a loop that we can loop over to train our model that updates the weights according to the loss. Now, admittedly, it's a bit lacking, one might say, right? Who wants to sit here and press a button over and over? And you're right in that. So this is where we can move to a slightly more enhanced training loop. So for epoch in range 100, right? So now we're defining a for loop that will iterate over this for us. And we'll just copy this over here. And now we'll let it run for us. And we can see here the loss is going down, which is sweet. That's looking good. They're getting pretty low of a loss. Now, admittedly, there's a few things missing here. One of them is the fact that we are not using our dev set at all, right? We always talked about how we split into our train set into a train and dev so that we can use our dev set to then know when to stop training. And you've seen all these images, and we talked about them in week 3, what a training curve looks like. You want your loss to decrease, but as your training loss starts to go down, but your dev loss starts to increase, that's how you know you're overfitting. So how do we do all of this? So we'll go up here and import matplotlib.plt pyplot as plt, right? And we'll use this for plotting. So let's go up here and we go create an array called lossy, in which we'll collect the loss at every epoch. We will initialize it to be empty. And then here, instead of printing, we will simply append lossy.append the loss value. And then when we're done training, we can do plt.plot lossy. This will get us a nice curve. Now I'll go up here and reinitialize our model so that we get fresh new weights, and I'll reinitialize our optimizer too. Make sure lossy is empty, and then run it for 100 epochs. So now we get a loss curve is what we'll call it. And we can run it for another 100 epochs, and let's go 500 epochs here, right? So this is a very nicely well-behaved loss curve right here. And we can see we're getting pretty low loss. Now, let's add in this dev set that we've been talking about, that we've been using before, to see when we start to overfit. So in our loop, we will evaluate on the dev set every epoch. Now, it's important to note that we don't want to use that evaluation to then go and update our weights. So we'll go with torch.nograd. So that means we won't be computing a gradient. We're just going to pass it forward and then evaluate our loss. We won't be computing that gradient because that's extra calculation for the machine, and we don't need that because we won't be propagating that loss backwards. So with torch.nograd, we'll call this dev underscore pred is equal to model, and we'll pass in xdev. Now, dev underscore loss is equal to, and then we'll use our criterion again, but now it will be between dev pred and ydev. And then we'll have to make sure that we create a new array to collect the dev losses. So dev lossy is equal to an empty array, and we'll go dev lossy dot append dev loss dot item. Now, one thing we should note here, and it's important, less so important for an MLP like here, but even here it's important if you start to use something like dropout, is switching your model from training mode to evaluation mode, and that's done via model.train is now in train mode, and then model.eval, and then evaluation mode, right? So let's look over this, make sure it makes sense. We're going to putting in train mode, clearing out the gradient, passing our train data set into the model, getting a prediction. Then we're calculating the loss, back propagating loss, stepping. The optimizer is updating the weights. We're appending the loss value to our lossy array. Then we're putting our model in eval mode. We're making predictions on the dev set, computing loss again, but now notably between the dev pred and the ydev. And then we will append the loss.item. Now, as you saw when we were going through this, now there's one thing that we should note, that we will likely get the same error if we don't put that there. And sure enough, again, the size mismatch. So we'll just go here and copy this. And now we won't get that error. Another thing we should note is plt.plot dev lossy. Now, we'll go ahead and run this and we'll see what it looks like. And then we'll go back and fix it if need be. Is the fact that we don't know which line is which, right? So here we can specify comma label is equal to, and then we'll specify lossy, loss, and then we'll go label equal to dev loss. Now we have to use plt.legend so that they show up, and to make it all proper, we'll go plt.show, which is not quite necessary, but it's good practice. Now we're running this, and you can see that the orange line is the dev loss, and we can see right here that our dev loss is starting to go up and our train loss is going down. And you can see it's starting to shoot up. So we're definitely starting to overfit around epoch, maybe 700. So we would likely want to stop at epoch 700. So let's do that. So this is what our loss looks like at epoch 700. And now let's evaluate our model on the train set. So model.eval. And then we'll do path model, and then we'll do x test. All right, that looks good. We're not getting any errors. Now we'll do this. Test pred is equal to model.xtest, and let's compute the loss. Well, let's not compute the loss. Let's just go ahead and look at our look at some of the metrics we used before. So we can go up here and borrow this from scikit-learn and go up here and import that. Now Notably, let's go ahead and try it, but we'll get some errors here. So classification report, and remember it's y true, y pred. So y true is y test, and then y pred is test pred. Now we'll get some errors here, and it says it doesn't like that they are tensors. It wants them to be NumPy arrays, but that's very simple. We can first detach them, and then we can turn them into NumPy. Now, we've detached them and turned them into NumPy arrays, and we're still getting this error. Classification report can't handle a mix of binary and continuous targets. So we might sit here and think what it is, but note that this is what our this is what our Y test looks like. It's a vector of binary values. But our test pred is not a vector of binary values. It is after sigmoiding. So that is not what we want here, right? We want it to be binary. So what we'll need to do is greater than or equal to 0.5. And now we get a mask. And we can do this. So you can see we get this Boolean mask. Now we can turn it into a NumPy, or we can turn it into a tensor or a NumPy array containing 0 and 1 in a few different ways. One of the simplest ways is we'll go over here and we'll take this piece of code and we'll go test underscore pred underscore npiece because it'll be NumPy. And then we'll go right here dot as type int. Now, let's just print this out to make sure, as a sanity check, make sure that's all good. So pretty much we're taking our test pred tensor, detaching it from the gradient associated with it, turning it into a NumPy array. Then we have a Boolean mask, and then we turn these bool values into integers, and we get something like this. Sweet, that's exactly what we wanted. Now we need to make sure that our testpred.mp will pass it into our criteria classification report. And as we had before, it looks better if we wrap it in the print. And sweet, we're getting a macro F1 score of 94 on our test set. So that is generally how you'll work within PyTorch. So a few things to note. Now, if we wanted to add more layers here, it'd look something like this. Self dot L1 is equal to nn dot linear. Now we got to make sure these match up. So maybe we do 32, 32, comma 16, and then we go 16 here. So this would be input layer 30, one hidden layer of 32, one hidden layer of 16, and then the output layer being 1. Now note, if you update the definition, you will also have to do it here because it will output different sizes and you'll get errors. So we'd have to go here and do x is equal to self dot relu. And then within that, we'll do self dot L1 of x. So now this will work, right? Because we have structured our L0, L1, and out to follow each other because of the sizes of the hidden layers we defined. So it'll work in the forward path. We can check that right here. Now, note that we're going to go here and take a look at this. And as we've said before, after you kind of evaluate on your test set, you don't really want to go back and change your model at all. But just for the sake of demonstration, we'll do that here. But this is not sound practice when it comes to training models. So you can see here, when we added that next hidden layer, we begin to overfit way sooner. So let's stop at 250 because we have a higher representational capacity in our model. So we redefine our model, and now we trained at 250. And now let's take a look at how this evaluates. And it looks like we're getting very similar results to when we had a bit of a smaller model. Actually, it looks like we're getting worse results. So now notably, you can see I'm rerunning it and we're getting slightly different results. And that's because every time we initialize our model, it is initialized with random weight. So you'll get slightly different results. But that concludes Notebook 3. Now, there's a lot more that we could talk about here from the theory side of things and also just from the coding side of things. There's, batches, batch norm, dropout, and, you know, all the types of networks that aren't simple MLPs. But hopefully this gives you a framework to build from because frankly, this right here is what's really important. This loop is already more on top of this, but this right here is the core, right? So every time clear, you clear the optimizer, then you do the forward pass. So then you compute loss, then you propagate loss, and you do opting step, right? So that right there, those will be your bread and butter, right? So you clear the optimizer, you do the forward pass, you compute the loss, you propagate the loss, and then you do the optimizer dot step. Now this line number 6 right here is for visualizing what the loss looks like, but this block right here is really important. So if you understand that, then from there you can build any network you want, right? So you'll go up here and define the model as you want, and it doesn't have to be an MLP. It could have, convolution, be a recurrent neural network, and then you create your training loop. And then as long as you were sound with your data split and you don't leak information, you've gone a long way and you've got a lot of good stuff to go. You got a lot of good stuff ahead of you. So that concludes number 3. Hopefully this lecture in general was helpful, right? So we're leaving with the idea of this is somewhat of a structured way you can approach your data. Now it will take much longer than this video right here, but feel free to reference it back or reach out to us with any questions. But thank you guys very much. It was a pleasure to be part of the workshop.